Welcome to this explainer. Today, we're diving straight into a medical puzzle where the exact sequence of your treatment is, quite literally, a matter of life and death. We're looking at a severe condition called diabetic ketoacidosis, or DKA for short. You know, in emergency medicine, it's not just about having the right medications on hand, it's about knowing exactly when to use them. If you get the sequence wrong here, well, the consequences can be absolutely catastrophic.
Our sources actually put it pretty bluntly. DKA kills fast, and the order of treatment is everything. And honestly, that's no exaggeration. Diabetic ketoacidosis is a rapid killer. When a patient comes in crashing from this crisis, the medical team is essentially racing against the clock. But here's the catch. Speed without the correct order means everything can go sideways in an instant. So we're going to explore exactly why the order of operations here is so strictly defined, and why deviating from it even just a little bit is incredibly dangerous.
All right, let's jump right into Section 1, the DKA crisis and its cellular failures. Because to understand the cure, we really need to grasp the cascade of failures happening at the cellular level.
So it all starts right here. The primary trigger is that insulin is completely MIA. It's absent. Without insulin, the body's basically locked out of its normal energy source. It's starving for fuel, so it panics and turns to an alternative, burning fat. Now, burning fat might sound perfectly fine, but in this unregulated, extreme context, it creates a massive byproduct. As the body rapidly burns through that fat, the bloodstream gets completely flooded with dangerous ketone acids. We're not talking about a minor imbalance here. It's a profound, rapid acidification of the blood that immediately puts the patient's life in jeopardy.
This massive acid load is tracked using something called the anion gap, which is a critical blood test marker. When those ketone acids flood the system, they drive this marker dangerously high. You can think of a high anion gap as a blaring red alert alarm for doctors. It shows exactly how severe the acid buildup is in the patient's body. The higher the gap, the more intense the crisis. The team knows they absolutely have to close this gap to save the patient. But as we're about to see, how they choose to close it is where the real danger lies.
Moving right along to Section 2, the potassium paradox. Let's look at the deceptive cellular mirage happening behind the scenes. We've talked about the acid, but there's a second major player in this crisis. While the blood is turning highly acidic, something else is happening at the exact same time. Because there's no insulin, blood sugar levels are absolutely skyrocketing. And this sky-high blood sugar acts like a giant sponge. Through a process called osmosis, it sucks water straight out of the body's cells. But that water doesn't leave empty-handed. As it's dragged out, it pulls vital potassium out along with it. Potassium is this incredibly important electrolyte that your cells, especially your heart cells, desperately need to function. And right now, it's being ripped completely out of its proper place.
Now, here's where things get super tricky. It creates this huge paradox. When the medical team draws blood for labs, the serum potassium, which is the potassium currently just floating around in the bloodstream, might actually look totally normal. Sometimes it even looks high. But the total body reality is completely different. Because all that potassium was dragged out of the cells and dumped into the blood, the lab results are effectively lying to you. They're masking a severe total body potassium deficit. The patient is secretly running on empty, even though that initial blood test says, hey, everything's fine.
And that brings us to Section 3, the fatal trap. This deceptive lab result sets up a deadly error for anyone treating the condition.
Okay, picture this. The patient has crazy high blood sugar, dangerous acid buildup, and the lack of insulin started this whole mess. It seems totally obvious to just attack the high blood sugar immediately, right? Your first instinct is to replace exactly what's missing. But ask yourself this, what actually happens if you administer insulin first right at this very moment?
Well, if you give insulin first, you trigger a massive immediate reaction. You see, insulin doesn't just lower blood sugar. It also acts as a cellular shuttle. It drives potassium back inside the cells. Because the patient already has that hidden total body deficit we just talked about, as soon as that insulin hits the system, all the potassium floating in the blood gets rapidly shoved back indoors. This happens incredibly fast, crushing the potassium levels in the bloodstream to dangerously low levels almost instantly.
And the crucial takeaway here is this, that sudden, extreme drop in blood potassium isn't just a minor hiccup. It can literally throw the heart into a fatal arrhythmia. The heart relies on a very, very specific balance of potassium to keep its electrical rhythm ticking properly. By giving insulin first, you crash the potassium, you disrupt that electrical rhythm, and the patient's heart can fail. The exact treatment meant to save them becomes the very thing that ends their life.
So, how do we avoid this? Section 4, the life-saving sequence. To bypass this deadly trap,
medical professionals have to follow a very strict protocol.
The life-saving protocol demands a rigid order of operations. Step 1, fluids first. The medical team typically starts with isotonic saline. This is absolutely crucial because it immediately helps restore circulation, rehydrates the patient, and actually begins to water down that dangerous acid load we talked about earlier. Step 2, before anything else happens, they must stabilize and confirm those potassium levels. They have to address that hidden deficit. Only after steps 1 and 2 are fully complete do we reach step 3, safely administering insulin to finally bring the blood sugar down and shut off the ketone production.
And this brings us to a magic number that doctors are always looking for, 3.5. You only safely deploy insulin once the patient's potassium is confirmed to be above 3.5 millimoles per liter. If it's below that number, you hold off on the insulin. You give them more potassium, and you wait until that vital electrolyte reaches the 3.5 safety mark. Only then is the heart protected enough to handle the massive cellular shift that the insulin is going to cause. Which brings us to this profound summary from our sources. Sequence is not a formality. In DKA, it is the difference between closing the gap and opening a crisis. The order in which we act is just as potent as the medicine itself. Following the protocol safely closes the anion gap and saves the patient. Ignoring the sequence, even with the absolute best intentions of lowering their blood sugar, rips open a massive cardiac crisis.
As we wrap up this explainer, I want to leave you with this broader thought. In complex medical emergencies, could the timing of your intervention be the ultimate life-saving tool? We always tend to focus on the miracle drugs and the flashy advanced procedures, but this DKA protocol proves that when you do something is absolutely, without a doubt, just as critical as what you do. Thanks for joining me to explore this incredibly vital medical sequence. Keep asking questions, and I'll see you in the next explainer.